Welcome to the second discussion for the
Lecture 2 material.
in ATM and 110. What I want to do in this lecture is I want to talk about the symbols we use to represent the things we are measuring. I also want to talk about the units we are measuring them in. That's really important. Now, I also really need to unpack engineering notation and metric prefixes. So metric prefixes and engineering notation are so linked together. And we'll see that in this video, in this discussion, you'll really get this. But I also wanted to say that if you want to jump into the lecture before this on resistor codes and components and a bunch of other stuff, what you can do is you can click on this guy over here. It'll have a link for this video, and so it'll have a link for the last video or lecture 1 or lecture A of this week. And also you will see a link to the third discussion in this week's lecture. Good. So there you go. And that's going to be about significant digits. It's huge. Significant digits is a really big deal. And measured values and the accuracy of other kinds of values. So how we write numbers down. And I'll also discuss in that video, in the second video, on how many numbers I would like to have in my lecture class. Let's just move forward and jump into symbols and metrics and prefixes and stuff and engineering. Let's just kind of unpack what we're going to talk about. We're going to talk about scientific symbols and units. Yeah, I'm like the unit freak. Yeah, dude, you have to put units in everything. If you write a number down, it needs a unit. Unless it's a unitless number, like a conversion factor or something. But don't write a number down anywhere. Don't type it into a computer. Don't write it on a piece of paper. If you're in my lab and I come over and I see you've written down some values and you don't have a unit, I'm going to lose it. Units are it's a ridiculously important thing to put in. A value is nothing without its unit. Cool. So enough about that. We're going to look at some basic electrical and magnetic quantities. So it's really important. Like magnetics are huge. So I want you to become familiar with some of those symbols because later in this course, we're going to like delve right into that stuff. And engineering and scientific notation. I want to teach you scientific notation just so you know not to use it, because we're studying engineering notation. And then we're going to just jump right into metric prefixes and switching notations, because you really have to know how to switch from scientific to engineering and I guess back as well if you need to switch into scientific notation. Maybe you're studying science. So that'll give you a better understanding of how these things work. And then we're going to take a look at measuring numbers and accuracy in our next PowerPoint that's in this week's lecture. Let's move on and just jump into these things and take a look at what's going on. I'm going to talk about kind of the bigger picture. And I'm going to step outside the SI system, but generally we're going to be using that for engineering disciplines. But essentially, we could be studying engineering in, let's say we go into pneumatics, which is a really big, it's huge in North America that we talk about PSI, pounds per square inch. It's not metric, it's not the SI system. So I need you to be comfortable I need you to be comfortable outside the SI system. But technically, I mean, that's what we're going to be using in electronics. So that's all I have to say about that. Let's move forward. These are the symbols used to represent certain things. So C, I don't know what that is. We'll go to that in a second. Q, that's so weird. What is Q? We'll go to that. Oh, I think I, everybody knows what I is. G is a good one. It's actually for conductance. Yeah, it's the symbol for how well something conducts. And there are a bunch of all of these other really cool things over here that we'll take a look at a lot later. R is one you definitely know. Actually, what's the one that's standing out here? Yeah, it's the F, the lowercase f. But to be exact about what I'm saying, because uppercase and lowercase actually make a really big difference. So, for instance, a lowercase v, we don't use that. Yeah, lowercase v is often used for velocity. Actually, we do actually use a scripted lowercase v to indicate instantaneous voltage. But generally, we're going to be using an uppercase v for the unit for voltage, and we're also going to be using an uppercase v for the symbol for voltage, but it's actually wrong. We'll get into that later. So what I'm saying here is, here's a lowercase over here. It's a lowercase f. That actually stands for frequency. Is that a unit or a symbol? That's a symbol. The unit is hertz. So we're going to unpack the difference between a unit and a symbol. Let's go on. Let's move on here. So this is just a whole bunch of stuff over here. Let's take a look at these. Oh, capital C is for capacitance. Okay. So some of you might have thought, oh, that's for a coulomb. Dude, that's what we measure charge in. That's a unit. and that's actually over here. So it's kind of weird that sometimes there are symbols and units that use the same character. In engineering, the symbol for energy is W. I know it's weird. You'd think it would be a capital E, but that's for physics. So depending on the discipline of study that you're looking at, sometimes they use different characters. So you can see that energy is W and it's measured in joules. Here's the thing with frequency. It's a lowercase f. It's measured in hertz. You can see hertz is a little bit of a different unit. It has two symbols to it. I mean, two letters in there. So you don't see that often, but I mean, you will see that, like in Webers. You will see Webers in a minute. Oh, look at this. There's another one. A uppercase W as a symbol is for energy. Yeah, I don't know why energy is a W, why they chose it to be a W, but I think it has to do with watts. I really don't know. I mean, I just know that they can't use E. The reason they can't use capital E is because that's technically, in the SI system, the unit for voltage. It's really weird, but we just don't see it. We use a capital V. I mean, that's what happens. So this is kind of a little game here that we could play. You can pause on this screen and you can look around to see where the thing is that's not, which of these is not a unit. And you can see these are both SI and they're imperial. I mean, I could put furlongs in here, which is not either, it's not imperial or it's not SI. I could put drams in here. What's a dram? Go look it up. It's pretty cool. Okay, good. So let's take a look at this. Magnetic units. Magnetic units and symbols are, I mean, they're fundamental in electronics. So you guys have to know this stuff. And you will know this stuff as we go forward. It's just a kind of a slide to say, look, there's a lot of stuff over here. And I did say that sometimes the unit has got two letters in it, like a Webers. And actually, another unit is actually called an amp turn. It's an AT, amp turn. So a lowercase t is for turns as well. So a lowercase t is for, this as a symbol, is for time. Let's go back up to here. A lowercase t for symbol is for time. Oh, it's not here. Okay. So a lowercase t, as you know, indicates time. That's the symbol for time. We measure time in seconds. Generally, we do that in engineering. We measure time in seconds. And I love this one, amp turn meters. Webers per amp turn meter. Oh, that's a really good one. Okay, this is a little bit of math here. We have to do the math with the units. I mean, it's just as important as a value. Just as important as a value. So we do math with the numbers, with the values. So let's do math with the units. So if I divide ohms by ohms, I get just the number. There's no ohms involved. If you divide a unit by the same unit, they cancel out. You do the math. Look at this. Just cancel out. It's kind of like this. How many pairs of eggs are in a dozen eggs? Well, the answer is not 6 eggs. It's just 6. I guess you could say 6 pairs. But it's not eggs. If the unit we're measuring in is eggs, how many pairs of eggs are in a dozen eggs? So you're dividing eggs by eggs. The answer is not 6 eggs. It's just 6. So keep that in mind. Another example here, I'm dividing volts by volts. There's just a number. It's not 5,000 volts. And by the way, can I put a metric prefix to this? Well, the answer is no, because to put a metric prefix, it's a before, it's a prefix. It's the prefix to the actual unit. If there's no unit, I can't use a metric prefix, so I can't say, well, that's 55, that's 5 kilo something, because it's not, there is no something. Does that make sense? There's another example, watts divided by watts. That's it, 500. Okay, there you go. Now, this is a pretty good one over here. We're still dividing units, but they have metric prefixes. So what do? Well, we can actually take this and convert it to engineering notation. We can convert that to engineering notation, but I'm just gonna kind of do it like this. I'm gonna ask you, what's the final unit here? If I divide this by this, I'm not asking you about the metric prefix. I'm asking you about the unit. What's the final unit? Well, you know what? Millivolts divided by microvolts is also just gonna be actually just a number. It's not going to have a unit because it's volts divided by volts. But if I really wanted to look at this, I guess I could say 250,000 microvolts divided by 50 microvolts. That would work. So there you go. Let's talk about powers of 10. I mean, you know this. You've learned this in science in high school or whatever. Let's just unpack it a little bit, okay? So we have this times 10 to the. And you're going to find that on your calculator times 10 to the, you're going to see two different things on your calculator. You're going to see a double E, you're going to see EE, okay? Or you're going to see 10 to the X. So what you can do is, if you had to type in a number like, I don't know, we'll go there in a second. I'll show you an example in a second. But here's just an example. 10 to the 3 is actually 1 times 10 to the 3, which is 1,000. And 10 to the minus 3 is 1 times 10 to the minus 3, which is 0.001. We'll just unpack a few of these as we go. Scientific notation and then engineering notation. We'll look at both of these. I want to define the difference between them because we have to learn to use engineering notation. We can't use scientific notation because we can't put a metric prefix to it. So scientific notation, it's a really convenient way, and engineering notation as well, to deal with really big numbers and really small numbers. So essentially, just moving forward and just take a look at these. I mean, you know how this works. Let me just show you an example. What scientific notation is, the decimal always goes after the first digit. The first digit, the decimal goes right away, bam, just like that. So as long as the first digit, the decimal, is after the first digit, then it's scientific notation, but it can be engineering notation as well. How does that work? Let's look at some examples. Okay, so some examples here. So 300, what am I going to do there? I have to put the decimal there. So it's 3.0, or just 3. And then I need to shift the decimal. I'm shifting the decimal. If I'm putting the decimal there, I have to multiply it by 2 zeros, or 100, to make it go this way. So I'm going to do times 10 to the 2. Over here, I'm putting the decimal there. I'm adding 3 zeros times 10 to the 3. Over here, I'm putting the decimal here. So it's 3.3 times 10 to the 4 because I have to move it 4 times. Over here, it's 2 times 10 to the 6. Nice. Okay, well, this is a good one. So that's 3.3, but I have to put the decimal here. So that's 1, 2, 3, 4, minus 4. Okay, 2 of these are engineering notation. Didn't I say this was all scientific notation? Sometimes they cross paths in that this is engineering notation because that's divisible by 3. This is engineering notation because that's divisible by 3. Let's unpack why that's true. So what's going on is that anytime we use engineering notation, we're going to have the multiplier either a 3, a 6, a 9, a 12, and then 15 and 18, and it actually goes all the way up to 24. So the other way around, we look at the other way, or we can go minus 3, minus 6, minus 9, minus 12, and blah, blah, blah. But it's got to be to a 3. Then it's engineering notation. The reason we do to the 3 is because that is 1,000, and another 1,000, and another 1,000, and another 1,000, and that's how metric prefixes work. They're always just 1,000 times more than the next one, or than the one before or after it. So we have to do that. Let's just show an example here. In engineering notation, whatever this number, whatever I'm going to put here, something time is going to be 22 or it's 2.2 or whatever it is, that has to be times 10 to the 3 or the 6 or the 9. In this case, it has to be 22 times 10 to the 3. It has to be, because I can't say 22.2 times 10 to the 4 because 4 is not divisible by 3. I can't apply a metric prefix to that. In this case over here, I have to put the decimal over here. I have to put 45 times 10 to the minus 3. But scientific notation tells me the decimal goes after the first digit. So in this case, it's going to be 4.5 times 10 to the minus 2. It's just a matter of practicing these and you'll get it. But I think this explains it okay. It doesn't get any more complicated than this. Just do some practice on it and you'll figure it out. So let's take a look at metric prefixes. Metric prefixes are in alignment with these values that are to the negative 12 and to the positive 12. And you see there are 3s. The scale actually goes up higher than this and lower than this. Generally, we're not going to look at those values. So we don't really need to look at them, and you don't need to really memorize them. But all of these you do, because we're going to be using all of these values. We're going to probably not tera, but the rest of them we're going to be using. I mean, you're here terabytes, right, in computers. That's what's going on there. That's actually a trillion. But you're going to see pico, you're going to see nano, you're going to see micro, milli, kilo, mega, and maybe some giga, and maybe some resistors. So these are all things you need to know in engineering disciplines. This is kind of a number scale. I have another number scale that I'm going to show you. So, but this is just another way of looking at it, and we can see tera, giga, mega, kilo, blah, blah, blah. What's in the middle? Something missing in the middle. It's just the base unit. The base unit doesn't need a metric prefix. So if we're measuring meters, we don't need, well, if we're measuring millimeters, we're going to times 10 to the minus 3. If we're measuring kilometers, that's 1,000 meters, so 10 times 10 to the 3. If we're doing meters, that's just meters. So how do we convert engineering notation into a metric prefix? Well, I mean, we've got all of these here. We know what the numbers are, and we can actually just replace this times 10 to the minus 3. Just replace it with milli. And this is an example here. So if that's what my calculator says, and by the way, if your calculator says that, it's not set right. We'll talk about that in a minute. But if that's what your calculator says, and you're calculating amps, well, then that's actually 25 milliamps. So your calculator should actually say 25 times 10 to the minus 3, or it should say 25e 10 minus 3, or 25e minus 3. All calculators are a little bit different. But if it's giving you engineering notation, it'll say something to the minus 3. And you know that that's going to be milli. So what you do is, as opposed to writing 10 times minus 3 amps, just write 25 milliamps. So I've had some students that actually write 25 times 10 to the minus 3 amps. Milliamps. They've written milliamps here. The thing is, if you're using a metric prefix, there's no need to use engineering notation. If you're using engineering notation, there's no need for a metric prefix. I mean, it's one or the other, because engineering notation is a little bit verbose. I mean, your calculator doesn't give you metric prefixes. Actually, that would be really cool if they had calculators that gave metric prefixes. I wonder if they had those. But anyway, your calculator doesn't give you metric prefixes. It gives you engineering notation. So when you write down the numbers from your calculator onto a piece of paper, you have to convert them to engineering notation. So if your calculator says, whatever, 25e minus 3, you don't write 25 times 10 to the minus 3 amps on your paper. Just write 25 milliamps. It's much, much simpler. Well, technically, I guess you can write 25 times 10 to the minus 3 amps. It's just silly. You don't need to go there. It's just doing an exercise here. Okay, so how many amps are in 1,000 milliamps? Well, milli is 1/1000th. So if you had 1,000 1/1000th, you have a whole, right? So that's 1 amp. Okay, down here. Okay, good. That's 0.115 1,000ths. No, yeah. Essentially, over here, look how many microamps. It's a big deal. It's actually 150 microamps. 150 microamps. So it's because the decimals over here. Microamps start over here. So there's 1, 2, 3. There's another 0, and then they start. So there's 150 of them. Let's just go on. I mean, you really should be looking at your metric prefix chart to be able to do this. So I don't know if you want to pull that out and just kind of pause this and pull that out so you can kind of guess these as you go. But you may just be good at this. Now, this is an interesting thing. There are 6 decimals between pico and micro. There's 6 of them. And the reason is because we're skipping nano. The reason I'm using this particular example is because for microfarads, or for farads, which is a measure of capacitance in a capacitor, we don't use nano. I don't know why. I mean, you can't buy a nanofarad capacitor. They just don't have them. They have 0.047 microfarads, or they have whatever, 47 or 470 or 470,000 picofarads. Like, it's really weird. I mean, it's like if it's in the range of nano, they kind of skip over it. They use either 0.01 or 0.00 something, or they use a number with 1,000 in it. I don't know why. I guess whoever makes capacitors just doesn't like nano anything. So there you go. We're looking at 0.063 microfarads. That's how many picofarads that is. This is easy. Okay, I think you guys know this. It's 2.67 mega. Okay, here we go. This one, whatever. This one takes a little bit of thought, right? But this is below. So we're talking about, this is less than 1 Henry. So we have to use milli. Well, how many millis is that? Well, it's 330 millis. Okay, this one over here, I think you guys are good with that. It's really no different from this one, and that is going to be 4.5. And down here, we've got 550 milliwatts. How many millivolts? How many volts is that? Well, in this case, we're converting just directly to volts. We're converting to a value that doesn't have a metric prefix. So in this case, we're dealing with less than a volt, because 500 millivolts is half a volt. So we're just doing a little bit over that. So 550 millivolts is 0.55 volts. So there you go. So that's a discussion about how these things work. It's just a matter of practicing these to get this good. Okay, reading your calculator. It's so important that you read your calculator, okay? You really got to get this. You have to know how this works. Okay, so let's just say you're calculating, okay? And you calculate current, and you do, and this is what the value on your calculator says this. What's the problem with your calculator? There are two reasons. I mean, there are two problems with your calculator. One is you haven't hit the ENG button. I don't have an ENG button on my calculator. By the way, this is my really old TI-81 that I had from like calculus. When I studied my first calculus class, I bought this calculator. That was in like the 90s, early 90s, maybe late 80s. I can't remember. But this is an old calculator, but it still works. It's great. I have the upgraded version as well. Graphing calculators are really good for calculus class because you can practice because you're doing a lot of graphing. So if you're going to do calculus, get one of these. You can't take it into a calculus test. So I have another one for sure because they're not going to let you take a graphing calculator into a calculus test because the test is pretty much going to be all graphing, or a lot of it anyway. Calculus has a lot of graphing. So what I'm saying here is that you got to have you're going to have a button that says ENG. Click, hit the ENG, or you're going to have a mode. This has a mode. So every single number I put in here comes in engineering notation. So if I put 0.00000001, what is that? Yeah, that's times 10 to the minus 9. That's what it says. That's the answer that it says. It doesn't say, I mean, it would be really cool if it gave me like a metric prefix, but it doesn't. Anyway, there you go. So if your calculator shows this, then you haven't hit the ENG button or it's not in the right mode. Fix it. We're studying engineering. I get a little excited about that. Okay, here we go. What's a metric prefix you should use? Well, it's times 10 to the minus 3. You've calculated value in milliamps. Okay, milliamps. There you go. So that's what's going on. Okay, after calculating current, okay, your calculator says this. Oh, that's like so bad. It's like almost evil because you know what? That's scientific notation. You have your calculator in the wrong mode. Get it out of scientific notation or leave engineering and go study science. We don't want you here. Right? Dude, you need this because metric prefixes, it's so important. It's wrong. Fix it. Good. What's the actual metric prefix you should use? Okay, so you've got to change this. This is interesting. You've got to change this to a 6 or a 3. What are you going to do? Which way are you going to go? Like, what happens if I change it to a 3? Where does the decimal go? Does it go this way or this way if I change it to a 3? Or how do we know? We've got this really good way of kind of figuring this out. It's a backwards number line, and I'll show it to you in a minute. But essentially what's going to happen is we're going to go to minus 6. I'm not going to go to minus 3. Because if we go to minus 3, I'm actually going to move the decimal this way. And then I'll be writing a number that starts with a 0. And that's kind of weird. Number lines. They help us tremendously to be able to figure out how to switch notation. But in this case, it's a backwards number line. I just kind of came up with this. It worked for me. I figured this out years ago when I was doing this myself. I'm like, how do I remember which way to go? I just envisioned a number line in my head that's backwards. Yeah, so if I'm moving down the number line this way, because I'm switching notation, I'm going from a 3 to a 4. Or from a 4 to a 5, or whichever way I'm going. On the number line, that's the way I shift the decimal. It's really simple. We just have to be able to envision a backwards number line. So let's just take a look at this. Okay, so I've got this. That is not scientific notation. It's not at all, right? So I have to fix that. So I have to turn that to a 6 or a 5. If I turn it to a 6, I've got to put the decimal this way. It's got to go that way. I can't do that because then I'll have a number that starts with a 0, which is just weird. Metric prefixes exist, so we don't have to use numbers to start with 0. So in this case, I'm going to have to go that way. So I'm going to go down to 3. I'm going to go from 5 to 3 because I can't go to 4 because 4 doesn't have a metric prefix, but I can go to 3. So I'm moving it 2 times this way, and I'm going to end up with this value here, 234 times 10 to the 3. Makes sense. Let's take another look at another one. So we've got this one, and I'm going to throw a number line up. So I'm going to convert this to minus 3. Okay, so I'm actually going this way because it's a backwards number line. So because I'm moving that way, I just move the decimal that way. So I'm going to take my decimal, and I'm going to move it twice this way, and that's just what it's going to be. I'm just going to move it twice that way. Okay, another one. Let's take a look at this one. Oh, I'm going to go from minus 9 to minus 6. Okay, that's this way. That's this way. So I have to take a look at that, and I'm just going to move the decimal this way. So I'm going to go 1, 2, 3. So it's 1.255 times 10 to the minus 3. Cool. So it's just examples. Let's just take a look at this, and we'll just go there. Now, what are we going to do about this one? Which way are we going to change it? In this slide, we're making the decision of which way to go. If I want to go to 6, which way do I have to go? Okay, I've got to go this way. Oh, that's fine. I can move the decimal this way. That's not a problem. It's good. I can move it, so it's great. I got 34.2 times 10 to the 6. Now, what about this one? 7.5 times 10 to 7.50. It's important to say that 0. If someone's written that 0 there, it's a significant digit. So 7.50 times 10 to the minus 10. Okay, so which way am I going to go? Well, I'm going to go to minus 12 because I'm going to go that way. I can't go that way. Right, so I'm going to go from minus 10 to minus 12. Okay, let's continue on. Ooh, 10.3 times 10 to the 2. So I'm going to either go to 3 or I can go to 0. One or the other. I can go to 3 or 0. If I go to 3, I have to go this way. I have to go that way. So I have to put the decimal that way one time. Just one time. If I want to go the other way, I'm going to go that way, and I have to put it twice this way. So I'm probably going to go to here. I could write 1030, and that's probably okay. I mean, let's say it's meters or maybe even ohms or some value that's larger. It's okay to just go there. So either way is acceptable in that situation. Let's take a look at one that you have to think about a little bit more. Okay, good. So I've got minus 8. I can go to minus 12 or minus 9, one or the other. If I'm going to minus 9, the decimal goes this way. If I'm going to minus 12, it goes even further that way. Okay, I can go to 6. If I go to 6, I've got to move the decimal 2 times, and it's got to go that way. So I'd have to go 1, 2. I can't do that because my decimal will be way over there. So I am going to go to 9, and I can move the decimal once that way. Does that all make that sense? I mean, this is switching notations. Guess what? You can forget about everything I just talked about. Just use your calculator properly, and it'll all be in engineering notation. Even if you type in 25.78e minus 7. Let's just do minus 7. So it automatically turns into minus 6 for me. Automatically. Just because this is an engineering notation. Get a graphing calculator because it's amazing. You can program this to do a lot of stuff. It's remarkable. Okay, here we go. So examples. These are just a whole whack of examples, and you can just walk through these. You can pause this slide, and you can just really just sit with these like, what's going on? You know, and do the same here, just more examples. And then you're golden. And as far as like a summary of everything we've just done, we know that scientific notation has a digit that starts right off the first digit. In engineering notation, that number, that multiplier number has to be a factor of 3. It has to be a factor of 3. It's huge. And that's it. Okay, bye.